Ladies and gentlemen, I'd like to welcome you all to the Geological Society of London and to this, which is the 9th Society London lecture for 2014, entitled Contaminated Land, What is it Good For? My name is David Manning and I'm the President of the Geological Society, and it's my very great pleasure to introduce today's speaker, Professor Paul Nathanail. Paul and I have known each other for many years because I have an interest in soils as well, and I have a particular interest in contaminated land from other points of view. So Paul and I have got much to talk about whenever we meet. But he's here as the person to talk this evening. Humanity has become a permanent geological agent. We see industrial activities, waste management, war, and accidents which leave a chemical fingerprint on soil and in groundwater. And this can occasionally threaten the well-being of humans and part of the ecosystem, various parts of the ecosystem. However, over the past 50 years, we've developed the ability to characterise, assess, and where necessary, mitigate the risks posed by such chemically challenged land, if I may put it like that. Virtually no land is so impacted that it must be discarded from any further use. Most land can be remediated where it makes environmental, social, and economic sense to do so. At the core of these activities of identifying what fate should come to land are environmental geoscientists. Environmental geoscientists are key members of the multidisciplinary teams that ensure that land affected by contamination is safe. Paul, our speaker today, is Professor of Engineering Geology at the University of Nottingham, and he's Managing Director of Land Quality Management Limited. He is internationally known for his applied research, for his vocational training and specialist consultancy work. He represents the Geological Society on the Specialist in Land Condition, the SILC register, as we call it. He's on their technical panel. He's a member of DEFRA's expert panel on contaminated land. Now, I'd also like to thank, before introducing Paul, RAW, you've seen the RAW group information that's out there on the table, who have provided the Society very kindly with some sponsorship, and we're very grateful to that. It helps these meetings go ahead. So without further ado, ladies and gentlemen, please welcome Paul Nathanail. Thank you, Paul.
I promise you I'm not checking my emails, I'm putting a timer on. Thank you very much indeed, David. Thank you for giving up your evening. It's my second run through this, so I know what's coming and you don't. But my mother-in-law was a copy editor. So I'm going to play around with punctuation. I'm going to talk to you about what contaminated land is, and hopefully conclude by reassuring you that it's good for pretty much anything you want, as long as you understand it and then manage the risks to deliver safety. And if you're into Twitter, I've copied the concept of a cluck, a complete lecture utterly compressed, from one of my colleagues in the University of Nottingham, and that's the whole lecture utterly compressed in 139 characters. It took me a long time to get it down to 139. I'm a bit miffed that I left one character unused, but never mind. The concept of housing and the need for new housing is obviously a very political hot potato at the moment. It's not going to go away from the front pages of our newspapers in the next 6 months or so. We expect our homes to be places of refuge, safety. Indeed, the guidance document on the front page, whose front page I have in front of you, co-published by the Chartered Institute of Environmental Health, the Environment Agency, and the NHBC, talks about guidance for the safe development of housing on land affected by contamination. And that's kind of the background context within which I want you to consider what I have to say. Now, I wear many hats. One of them is as a director of a European network on brownfield regeneration called CABERNET. It's a great acronym, and it's a fantastic excuse to travel Europe talking brownfield reuse and sampling ethanol contaminated groundwater. The ABC model you see in front of you was put out about 10 years ago to help us understand the trade-off between the cost of reclaiming, remediating land, and the value it has afterwards. The CABERNET A sites are where you make profit. The Cabernet C sites are where the costs are so high that even post-remediation, the land isn't commercially viable. And the B sites are the marginal ones where the public sector can come along, provide a bit of intervention, and then that will facilitate private investment to come in and bring land back into use. Now the quote up on the right here, buy land, they're not making it anymore, is from Mark Twain. And that's pretty true, except I used the quote in the Netherlands and they said, doesn't apply here. Over the last couple of years, I've been working with colleagues across Europe on a European Union funded project on brownfields and the circular economy. And we've begun to look at the trajectory of sites on this ABC plot. If you can reduce the cost of reclaiming the land and increase its value, then you get extra benefit. However, if you get it wrong, you can spend extra money and actually reduce the overall value of the land, and that's a no-win situation. What we're actually looking for, though, are ways of magnifying and amplifying the value out of more synergistic uses of land. So looking at dealing with the risks, while at the same time creating new opportunities for energy generation, energy recovery, creating space to use. The context is within one of urban land management. How do we run our towns, our cities, our villages in ways that are smart, ways that are going to stand the test of time? And what we're trying to do in Ombre, that's the name of the project, it's not quite as good an acronym as CABERNET, is it? Is to decouple the way we manage our land, the way we use the land, and the way we manage it, the way we make decisions about it. At the moment, we're involved in a single circle where you use your land, it comes to the end, you scratch your head, come up with a new use for it, and the land lies unemployed for a while. And that's wasteful. That's a resource inefficient way of doing things. So we're trying to decouple the two gears of the wheel, if you will, because the management circle can operate more quickly than the land use circle, which operates on timescales of 20, 30, 200 years even, if you look at this building. So what is risk-based contaminated land management? I'm going to kick off with this before I talk about a few definitions. Risk is about the product of hazard and vulnerability. Something happens, it could be a landslide, it could be the presence of contamination, and something can be damaged by it. Or it could be the probability of something adverse occurring and the consequence of that bad effect happening. Well, in contaminated land terms, we're interested in risk in terms of the link between the source of contamination and its potency, is it arsenic or cadmium, the receptor, the thing or the person we're trying to protect, could be an ecosystem, it could be a building, it could be us, it could be our groundwater, and how those two can be connected by one or more pathways. If there is a risk at a level at which the risk is deemed to be unacceptable through particular legal lenses, then you've got to manage it. And you can manage risk by dealing with the chemistry, dealing with the source term, or interrupting the pathway, or managing the behavior of the receptor or the use to which you're putting the land. So if you can break that relationship, you've reduced the risk. And it's about managing risk, not molecules, that risk-based contaminated land management is all about. But what is contaminated land? Contaminated land is a legacy from the past. It's an externality from historic industrial operations. The consequences of pollution should have been dealt with at the time, but they weren't. The profits from industry at the time should have dealt with it, but they didn't. It's been left to us. Or it's a result of the way we've managed our waste in the past. The accident, the occurrence of industrial accidents, spills, explosions, that sort of thing, or indeed the consequence of war. All of these have led to land contamination. On the left, you have the formal legal definition of contaminated land. It's laid out in Part 2A of the Environmental Protection Act of 1990. And on the right, there's a more colloquial understanding of what the term means. So the formal definition of statutory contaminated land, well, first of all, the local authority decides whether land is contaminated or not. And they're looking for substances that are either causing significant harm, death, disease, and so on. Or there's a pretty big chance that if nothing is done, that kind of harm is going to happen. Or controlled waters, groundwater, surface water, lakes, ponds, and so on, are being polluted to the extent that really matters. Or again, if nothing is done, that kind of pollution will happen. So that's on the left-hand side, the formal definition. On the right-hand side, the kind of street definition, or the street understanding of the term is, you know what, this land is chemically challenged. It's got stuff in it it shouldn't have. It's got chemicals that are dangerous, usually put there by us. It's potentially harmful, dangerous, carries a high risk. To differentiate the two, we in the sector call that statutory contaminated land and that one land affected by contamination. It doesn't quite roll off the tongue, and it certainly uses up more characters in a tweet than I could afford. Well, why does it matter? On the left, you've got a long list of high-profile sites where contamination was an issue in the UK at the bottom and across the world at the top that led policymakers, public health protection people and so on to realise that there was an issue here that needed to be dealt with. Minamata, the third one down on the list, is ultimately what gave us the Convention on Mercury that was signed at the beginning of 2014. On the right, you see the establishment trajectory of different attempts to recognise and develop a policy on land contamination in the UK. That all culminated in this document in 1994, 20 years ago, which laid out a framework for contaminated land that then informed both legislation, policy, regulation, and a lot of technical research to support those. What you don't want are headlines like this. This is an image taken from a newsletter of what was the Health Protection Agency, is now Public Health England, and it shows you the kind of ways that contamination is reported in the media. This is what happens if you get a gas explosion. And I'm very aware of the close escape a father and his daughter had yesterday in Southampton from what seems to have been a mains gas leak. The explosion at 51 Clark Avenue, Loscoe, was not mains gas. It was landfill gas. The geological cross-section shows the geometry. Here we have the landfill, nicely capped to stop any gas generated by the decomposition of waste from escaping upwards. So gas flows along the bedding planes, up dip, finds its way into 51 Clark Avenue, and then some kind of ignition causes the explosion that you see here. We see the geology acting as a source of contamination, and then the pathway along which the methane, the explosive gas, finds its way into the property. The people in 51 Clark Avenue were injured, but fortunately there were no fatalities. Erin Brockovich made her name as a paralegal in the United States, and the film won Julia Roberts an Oscar. The consequences of the release of hexavalent chromium into the community around Hinckley resulted in a court case that resulted in $350 million compensation to the plaintiffs, and that didn't include the court costs and the remediation costs. Back home again, the public water supply borehole of Cambridge Water was polluted by solvents used by a tannery. The solvents over a number of years were spilt into the ground. They sunk down in the ground. Denser than water, they sank through the groundwater and eventually found their way into the public water supply borehole, which then failed water quality tests, had to be decommissioned, and a new one had to be built somewhere else. Here we're seeing the geology acting as the pathway, and the groundwater itself is a receptor. This one ended up as a case that was heard by the House of Lords. So how do we go about managing land contamination? Well, we begin at our desk. We're trying to understand the history of the site. How was it used in the past? What kind of industrial land uses were there? What's the geology? What kind of regulatory actions were taken? We then visit the site to see what's there today, what condition is it in, and to see also basic logistical things like how am I going to get my drilling rig in there if I need to do a site investigation. At the end of the phase one, you end up with a whole load of stuff that you know and a whole load of things that you don't know that then become the objectives for going out and taking samples. drilling boreholes, excavating trial pits to get soil, water, vapour or gas samples that you get analysed to understand the geology and the chemistry of the site. At the end of that, you carry out a risk assessment to see whether the patient is ill, to diagnose whether we have a problem. If there is a problem, then you move on to phase 3 to manage the risks by, and my slide here illustrates the construction of a barrier that isn't solid. Groundwater continues to flow through that barrier, but as it flows through, it gets treated, so you have dirty water flowing through and coming out clean before it drains into this surface water body. We call that a permeable reactive barrier. Or you can interrupt the pathways in the made ground, or indeed you could, but I haven't illustrated on the slide, deal with the contamination itself. However you do it, the point of the risk management exercise is to demonstrably break that relationship between the source of contamination, the pathway, and the receptor. And the key word is demonstrably, because you haven't got it documented, you can't convince the regulator, residents, lenders that the job's been done properly. Now, we've been aware of the impact of our activities for a long time. This is an extract from the Public Health Act of 1875. The original is on the left here. You can get it on the internet these days. And then on the right, I've just got some extracts. In those days, we had an inspector of nuisances who went out and inspected the area of his urban authority, and where he found an accumulation of manure, dung, soil, or filth, or other offensive or noxious matter that ought to be removed, he gave notice to whoever owned that stuff, who then had 24 hours from the serving of that notice to remove it. If that material was not removed, then the urban authority acted. It could keep the money it made from the dung, soil, filth, or other offensive matter. And if there was any surplus, then the owner could claim the surplus back. Those were the days. Moving forward to 1994, this is the outcome of the consultation on contaminated land by the then Department of the Environment. Consultation document back here, and then this is the outcome in late 1994. 1994, 20 years ago. The government is committed to sustainable development. Pollutant pays principle. Their priority is to prevent or minimize further pollution of the land. A bit like first aid, stop the situation getting worse. Then they wanted to make sure that land was suitable for use. If you're going to use it for a housing development or a kindergarten, then you need to make sure that the levels of contaminants are low so that the risk is low. If you're putting a car park or a commercial office building on there, the risk levels have to be the same, but the chemicals can be at higher concentrations because the exposure is lower. So we're looking at suitability for use. They wanted to either return land to beneficial use, and we had plenty of spare industrial, post-industrial land in the early 1990s, or keep it in beneficial use wherever practicable. Now, it's also a fairly pragmatic approach that soon became widespread across Europe and indeed beyond. It would be neither feasible nor sensible to try to deal with all the land at once. The wealth-creating sectors of the economy could not afford to do so. However, the urgent and real problem should be dealt with, but in an orderly and controlled fashion. That led on to legislation, policy, regulation, and science. So, risk-based land management is this bit. But my risk-based land management sandwich includes risk communication at the start and at the end and throughout. So risk communication is making sure that people who are interested in the process and its outcomes and the decisions, A, are aware of what's going on, B, have a say in how the decisions are arrived at, and C, are told what's going on at all stages. So risk-based land management is about deciding whether there is a problem, whether there is a need to remediate. Is the patient unwell? And then if he is, you carry out an operation, you remediate, you try and make them better. And the question then becomes one of, when do you stop? How much remediation is needed? Well, that depends on the level of risk that your site is posing, not on the total concentration of your contaminants. So we're in the game of risk management, not molecule management. Geology can be a source of contamination, heavy metals in the ironstones, for example, hazardous ground gases, methane, radon, carbon dioxide, or organic contaminants. It can also be a pathway to allow fluids and gases to migrate, or it can be a boundary, a barrier, and stop lateral migration. It can also be a receptor in its own right, principally through groundwater, and perhaps also affecting sites of geological interest. The way that we go about looking at the risk assessment involves beginning with the legal context. That's a bit like the exam that university academics like to set their students. So rule number one in an exam is read the question. Rule number one in risk-based contaminated land management is establish the legal context that you're doing the work under. You then go through a process of formal risk assessment, which includes 4 steps: hazard identification, hazard assessment, risk estimation, and risk evaluation. Hazard assessment is from the history of the site and your walkover and so on, what substances do you expect to be there? Then you need to work out how they're going to behave. How will they migrate through the subsurface? What happens if they get to the surface? Will they be a liquid or a gas? Will they degrade? Will they stick to the clay particles? And then finally, so we've got fate and transport, and the third component is their toxicity. What happens if they're entering into an organism? If they get into us, or a plant, or an animal of some sort. That then allows you to estimate the risk to receptors that are valid given the legal context. Having worked out the risk, the scientist's job is done. The final stage is to evaluate whether that level of risk triggers a need for remediation or not. And that's not a scientific question. It's a socioeconomic question that reflects our willingness to tolerate risk, our ability to pay to get it removed, our ethics, our morals. So this is not a scientific question. So that's the process of risk-based land management. The key tool that we use to do that, to understand what the problem is, and it's a spatial problem, is the conceptual site model, which includes plans, topological diagrams like this, and it gives you the relationship between sources, pathways, and receptors. So I'm going to talk through 7 principles of contaminated land management to deliver the kind of safety and security that we want. Pictures on this slide show Love Canal in upstate New York. William Love was an entrepreneur who decided he was going to power his utopia by digging a canal and connecting Erie and Ontario, and using the height drop between the two to generate DC electricity to power his utopia. Problem was he got overtaken by technology, and AC superseded DC electricity, so his canal was unfinished and his dream never came to fruition. The canal became a landfill of industrial waste. The land after the Second World War was sold to the Board of Education, who built a school and houses on the area, and then people were being exposed to or coming into contact with contaminants. The area was declared a federal emergency by President Carter and led to the US legislation that is technically called the Circular, commonly known as Superfund. So the 7 principles, and all the principles have got this kind of bamboo font. Every risk assessment is a site-specific risk assessment. There are generic approaches that we take, there are generic tools that we use, but you've got to understand every site on its own merits and make decisions about each site. So later on, I'll talk to you about a fairly detailed approach to risk assessment. But on this East London estate, we did a detailed quantitative risk assessment after somebody else had recommended remediation was necessary. And we showed that 7 to 30 million pounds, depending on which estimates you looked at, didn't need to be spent because the site was okay as it was. We spent a few £100,000 proving that, but the payback was very good. Mortgage lending resumed, and so on. Principle number 2, the legal policy or policy context is the starting point. We have 2 big contexts in this country. There are others as well, but the main ones are the planning regime, making sure that new houses are safe, suitable for use, and then Part 2A, which kicks in and looks at the existing land use and says, is that okay or not? If it's not okay, if the risks are high enough, then there is a statutory intervention, a remediation notice, a bit like the one that would have been served by the Inspector of Nuisances in 1875, is served on either the polluter or the current landowner to reduce those risks. Now let me just explain that in a little bit more detail. My house has central heating in it, and it's heated by a gas boiler. The gas boiler's been in there for over 10 years. Works fine most of the time. If somebody came along today and said, I want to install a new gas boiler, the gas boiler that I've got there would be illegal to install today. So standards have moved on, technology's improved. So if you're going to come in today, you'd be installing a new, safer gas boiler. But the gas boiler I've got isn't sufficiently dangerous to merit its removal and replacement. Were it so, I would be required to take it out and replace it with something modern. Equally play that analogy with cars and safety belts if you want to. So to assist that process of risk assessment, we have worked to develop screening values. The latest edition comes out next week. They're called Suitable for Use Levels, S4ULs, and we've developed them in partnership with the Chartered Institute of Environmental Health, the professional body for environmental health officers. Now these are soil screening levels for about 85 substances that represent levels of risk that are negligible or minimal. They comply with guidance from the Environment Agency, DEFRA, Department of Health and so on, and they reflect 6 different land uses, and they're published as a book that people are allowed to use for commercial, consultancy, regulatory purposes. We'll come back to numbers a bit later on. But this is just the shopping list of substances that we've covered. There's about 85 on here. Metals, petroleum hydrocarbons. PAHs are what you get too much of if you burn your burgers, if you're having a barbecue in the summer. Phenols, explosives, various types of solvents, pesticides, a couple of oddballs here. Principle number 3. You can't manage what you don't understand. The way we communicate our understanding of a site is through the conceptual site model. On the right, you have the title of an appeal decision by a planning inspector for a site which was refused planning permission. One of the reasons that he gave for refusing it was there was no conceptual site model, and therefore the level of risk was not demonstrably low enough to render the land suitable for use. So a conceptual site model should show you where your sources of contamination, pathways and receptors are, and the uncertainties that are remaining about your site. These are the uncertainties which will become the objectives of the next phase of investigation if they are driving the decision. What does it look like? Well, it consists of a map, a cross-section, a topological network diagram, a bit like the London Underground map, and just tables of text information. So there's my map. Cross-section. And my network diagram showing the topology, the connectivity of sources, pathways and receptors. So sources connected through these pathways to those receptors. Or on a clever piece of software that you can have a look at later on. What we're trying to do is to make decisions. Now, this is the front page of a guidance document called Good Decision Making Guide by the Queensland Ombudsman. The Greek at the top from Socrates says, the only thing I know is I know nothing. And the Ombudsman kind of summarizes that by saying the gathering of relevant information is a crucial factor in good decision making. Now, the relevant information in this case are the uncertainties in my conceptual model. They're the things that I ought to know, should know, but don't know. And those are the things I go out and drill, construct boreholes, take samples and so on to reduce those uncertainties because they're relevant. I don't need to know everything about my site. I need to know what I need to know about my site. I need to know what's relevant. Principle number 4, begin with a qualitative risk assessment. Because if you ask the wrong question, you'll get the wrong answer. Numbers such as the screening values I showed you before, are important, but they're not enough. They need to be used in the right context. So this is a picture of a contaminated site that we're investigating, and I'm going to look at this area next to the skateboard park, and you can see at the surface this black tarry stuff. I don't need to get that analysed to know that there's a problem there, because I've got a source of contamination at the surface and I've got children playing in the area, so I don't need to go any further than that to know that some kind of remedial action is needed. Just to the right of this picture, just to the right of that structure, there is an allotment garden. And the issue here is whether the produce that's being grown in the allotments is taking up enough contaminants in the soil to render these dangerous to human health. Now there I do need to take samples, I do need to get some numbers, and I do need to do a quantitative risk assessment. But the qualitative risk assessment is always your starting point. Principle number 5, don't save money at the site investigation stage, save it at the remediation stage by doing a decent risk assessment and knowing how far you need to go and going no further. Now, 25 years ago, my first ever presentation in this room was after a Department of the Environment research project on adverse foundation conditions. And in that report, we had a little cartoon that showed some ground engineers looking at the Leaning Tower of Pisa. And of course, it shouldn't have been leaning. And the caption to the cartoon says, you always pay for a site investigation whether you have one or not. It's not true. You pay for more than a site investigation if you don't have one, because things go wrong. So this is not the time to save money. You need to have smart objectives to remove the uncertainties in your conceptual model. And by smart, I mean specific, measurable, achievable, realistic, and time-bound. So that when you go out and take samples, you know why you're sampling, what you're sampling, is it the soil, the gas, the water, where you're sampling, horizontally and vertically, and how you're going to take the sample, store it, transport it, and so on, because that will affect what the chemical laboratory can do with your sample when they receive it. Or maybe you should have done the testing on site in the first place. Next 2 or 3 slides talk about specific issues that kind of feed into that decision-making arena. In March of this year, we published the first new guide on asbestos in soil and made ground for 24 years. Published by Syria, the Construction Industry Research and Information Association, and really it boils down to try and help us understand how to characterise and then manage risks from asbestos that might be contained in near-surface soils on our construction sites. So as a geologist, I am normally interested in what there is in the soil, the asbestos content. But actually, that really doesn't matter that much. I'm more interested in the fibres of asbestos that there are in the soil. And actually, of those fibres, I want to know which ones can become airborne and then dispersed through the air, breathed in by somebody, so I can calculate a cumulative exposure over a number of years that I can then compare against my epidemiological data that tells me what level of risk a particular level of cumulative exposure to a particular asbestos type poses. So asbestos is strange. This slide has a whole masters on one slide. But if you know your Toblerone chocolate, then you might remember Tobler's law of geography. Things closer together are more similar than things further apart. That's the way he characterized it. The variogram is a way of trying to quantify and understand in detail this law. So the axes. The axis along the bottom, the x-axis, is about how far apart things are. The y-axis is a measure of difference. It's like a measure of variance. So things at the bottom are not very variable, they're pretty similar. Things up here are very variable, very dissimilar. So this is a variogram for a particular study from lead in soils that we published a few years ago now. So look, at 60 apart, the value is at about 35,000. Double that, go to 120, we come up to about 42,000. go up to 180, and we've got 49,000. So this is quantifying what closer together means down here, and more similar means. So the lower down you are on the y-axis, the more similar you are, and the smaller the x-axis is, the more close together things are. Now, contamination is a spatial problem. The use of non-spatial statistics, classical statistics if you will, can therefore lead to errors. Because if your contaminant occurs like this, and you've got rich zones and poor zones, this is where the spill was or the accident was, and this is some distance away, then calculating non-spatial estimates of means or upper confidence levels and so on doesn't help, because you've got high areas and low areas. Imagine you had a private pilot's license and you're flying across the Alps. Do you want to know what the average height of the Alps is? Or do you want to know how high the peaks are? If you thought the first one, remind me never to accept a lift off you in your private jet. So we are dealing with a spatial problem. We need to recognize that and recognize that the questions we're asking will take us down one route of analysis rather than another. And in fact, this afternoon, the Society kindly offered us space to have a discussion on a draft international standard on sampling statistics and sampling strategies, and a large part of the discussion revolved around how do we handle spatial data like this. I mentioned my site in East London. When a child is in the back garden and they get dirt on their hands and they lick their fingers and they ingest soil, some of what goes in comes straight out the other, well, not straight out, but a bit later on comes out the other end. The ratio of what goes in to what ends up in the bloodstream and is then able to go and do some harm is the bioavailable fraction. Most of our soil screening levels, like the ones I shared with you a few minutes ago, assume 100% bioavailability. So if it goes in, it can cause a problem. Now that's fine generically across the piece, but on a particular site, that's a very, very over-conservative assumption. So by looking on a site-specific, soil-specific basis, you can calculate how much of the soil is going to dissolve in your bloodstream and how much it will pass through, and you can use that to modify your risk assessment. Let me give you an analogy. Think of the generic assessment criteria, the soil screening levels that you can use anywhere across the country, and if you're below them, you haven't got a problem. Think of them as off-the-peg suits. They'll pretty much fit anybody, but not particularly well. They'll do the job. It's fine. There's nothing wrong with them. But if you really want one that's tailored to your lumps and bumps, you go to Savile Row and they measure you up and they make one that will fit you perfectly. Bioaccessibility is one of the ways that we refine our assessment criteria to better reflect the conditions at our particular site. So we're reducing uncertainty, reducing the cost of reclamation, if you remember my CABERNET ABC model, to deliver the safety that we're after. Principle number 6, write for your reader, not your lawyer. The temptation to conclude a report with get more information has to be resisted. Jargon in any subject has a role to play. It's unavoidable. But at the very least, define what the words mean up front so that your reader can follow your logic and understand where you're going and how you got there. As either regulators or developers, you have to make decisions, and as consultants, geoscientists have to inform and help advise that decision-making process. So not deciding actually is a recipe to decide to get it wrong and fail. In writing that kind of quite heavily technical report, it's difficult to get a balance between accessibility and readability and technical robustness. So often, short executive summaries that are plain language really help get the main message across. And if you want to know how you got that message, then you've got to wade through the more technically difficult stuff. It's difficult, it's hard, it's time consuming. And it was Winston Churchill who began a letter by apologizing that the letter was so long. He said, I didn't have time to write you a shorter one. So I'm not downplaying the difficulties, But after you've done all the hard work, clear, simple, short summaries can help get the message across. The whole context is one of management. It's about making decisions. And then having made the decisions to implement the solution that you've identified, and that needs a sound understanding of your site and a good capture, a good grasp of the legal context and the socioeconomic context within which you're looking at your problem. So since we're making decisions, we need to try and see whether we can get the decisions right. If you get them wrong, there are two types of error you can make. You can wrongly say that land needs to be remediated when it didn't. So you undertake unnecessary remediation, you waste some money. Or you can wrongly say land is okay, it doesn't need to be remediated, and leave behind a dangerous situation. Clearly, that is unacceptable. The decisions that we're making under planning or Part 2A are asymmetric. Under planning, the developer's task is to demonstrate the land is safe. So the level of risk is low, and they've got to show that the land is under that low level of risk. Part 2A, the local authority comes along and says, this land is so dangerous, you need to do something about it. The level of risk is high, and the local authority has to demonstrate that you are above that high level of risk, and therefore a remediation notice can be served on you. So a good decision must be consistent with the law and be a reasonable one on the back of the evidence that you have to hand. Getting it wrong, where you do a bit of unnecessary remediation, may be unpalatable, but it's a much easier pill to swallow than getting it wrong and leaving unremediated a dangerous situation. So risk assessors are not aiming for a bullseye. That's the scenario that we're in. If we get it wrong one way, well, it's not the end of the world. But if you get it wrong the other way, it's a bit of a rough message to go back to Mrs. Tell and say what happened. But I want to step back a bit and go back to my houses and even bigger than that, because principle number 7 is about effective regeneration and preparing places for us, for people. This is the market square in Nottingham, getting ready for a fair. And that's not rain, that's a water feature that is very good for capturing reflections of the town hall there. What does that regeneration mean? Well, it begins with the remediation, the breaking the risks that I've been talking about. It includes reclamation, making the land physically okay, refurbishing buildings, recycling construction material, crushed concrete and so on, redeveloping the site, and then bringing life back, revitalizing the site and creating a new economy and a new community. That's the O2 Dome. I was there on the 1st of January 2000 with my family. We had a lovely day out. But that year didn't go very well for the dome. Today, so all this stuff had been done, and they were missing this bit. Today, it's one of the most popular music performance venues in the world. Success. So our job is important, but it's not the complete part of the story. To deliver those kind of achievements, you need to understand the urban system that you're sitting in. So this is some work we did from the Ombre project that just finishes next week. It's trying to understand urban systems by looking at the way environmental, social, and economic factors interact with each other. So you change the system by building an O2, how's the system going to respond? And it allows you to understand the system well enough to predict which elements of your neighborhood, your city, ought to be disturbed to bring about change that you're interested in. The approach was developed by Professor John Hudson of Imperial College a long time ago, and I applied it to an open cast coal site as part of my PhD work when I was working for Wimpy when they were a construction company. And we've now applied that to urban land management and trying to understand towns and cities. So our role in that whole area is to reduce the risks from the chemically challenged land by dealing with the source, interrupting the pathway, or protecting the receptor, or putting some kind of institutional control in there. If there's no linkage, there's no risk. The risk can be reduced by remediation processes that include pre-processing, getting the ground ready, treatment, breaking that linkage, and then post-processing, dealing with any byproducts, wastes, and arisings from the treatment. So just an example. Air sparging involves violently blowing air through the groundwater so that any dissolved benzene, toluene, volatiles come out as vapors above the water table, where they're sucked out by a vacuum that's applied to the soil, brought out to the surface. Job done. You've removed the contaminant, so you've broken that linkage. And then the vapors are put through a granular activated carbon filter that captures them, a bit like the carbon filters you may have in the hood above your hobs at home in your kitchens. So how do we choose what kind of remediation to do? Well, the risk assessment is where we decide we need to do some remediation. We can then shortlist a number of technically feasible strategies and then choose the one that will achieve the job, that will achieve the remediation objectives, and do so by optimizing the social, environmental, and economic value of the works. And we call that sustainable remediation. This is the front page of a committee draft international standard on sustainable remediation, and I chair the working group that's developed that. The consultation window for that document closes tomorrow, so I'm hoping within 12 months or so we'll have a published international standard that will be used across the world to help understand what sustainable remediation looks like. So I hope you're beginning to get an appreciation that what we're dealing with is multidisciplinary. That's us, the geologists. We have lawyers, environmental health people, biologists, chemists, surveyors, toxicologists, planners, engineers, all of whom the contaminated land manager needs to decide when and how to draw in to help understand and resolve the issues we've been talking about. So I'm going to leave you with the thought that it's a good career if you're interested in variety, a challenge, combination of site work and office work, preferably in the sun and back in the office when it's raining. Doesn't always work that way. Working in business, doing something useful, cleaning up land or protecting land. And it's also useful if you enjoy a bit of chemistry, a bit of maths, handling data on a computer, rummaging around old archives, understanding the law, and being a bit of a detective. So, contaminated land, what is it good for? Well, actually, it's pretty good at presenting and preparing and delivering planet-friendly places for us. And I'm hoping that my complete lecture, utterly compressed, now makes a bit more sense. Risk assessment and management renders contaminated land in the broad sense, sensu lato, as suitable for reuse, and the local authorities get the high risks remediated. Thank you.
Well, thank you very much, Paul. The tip of an iceberg of a career's worth of experience there. I really appreciate the insight that you've given to us. Paul is happy to answer questions, and because the proceedings are being broadcast, it would be good if you have a question, if you can wait for the microphone to come to you, and then put your question then. So who would like to kick off? Yes, the lady here, please.
Hello, thank you for that. It was a smashing talk.
Thank you.
Where there have been industrial processes going on, like gasometers and gas production in previous decades, and those have now been closed down, land has been covered over, from my own reading of local papers and things like that. Land has been covered over and housing has been built. Is that information kept at the land registry so that when people are buying those apartments, that information can be given out?
That'd be a really good thing if we did it, but we don't. The information where it's stored will be in the planning records for those properties, because in order to get permission to build houses on a former gasworks, to give you an example, you would have to submit a site investigation and a risk assessment that says we're going to build the houses, and in part of the building them, we're going to break the linkage. In your case, you've talked about putting in a capping layer. So That's the evidence base that would be needed to be seen by a prospective future buyer or lender. So the short answer to your question is, it's not in the land registry, it would be in the planning records of the property held by the planning authority. The extent to which that information is curated in the long term varies from authority to authority. I've done it myself and gone and looked at properties and seen site investigations from 1945-46, and I've also been to authorities where they had changes of boundaries, and in order to save space, they've got rid of their old archives. Nowadays, many site investigations are put on planning portals, so actually it's easy for us to access that information today, but the shelf life of that information is anybody's guess in terms of the long-term curation of that sort of information. So it is an area where the UK could actually do with improving its long-term appreciation of the value of information like you've talked about. The historical information about the gasworks being there is easily findable. It'll be on historic maps and so on. You can see that there are houses there now, so you can look at the spatial juxtaposition of potential hazard and receptor, but the fact that the problem was recognised and dealt with isn't always as easily findable as it could be or should be.
Thank you. Any further questions? Yes, please. Back there, and then we'll move over here.
Thank you again, Professor Nathanail. You put a slide on the presentation which showed a barrier, a wall,
yep.
Which was the intercepting wall for preventing contaminants from passing beyond it, but maybe the water continues, but a lot of the contaminants are removed. What sort of matrices are being used in this day and age? You mentioned activated carbon, etc., but are there other things? I'd just be curious to know.
It depends on what the contaminant is. I mean, the classic example is you've got solvents dissolved in the groundwater, chlorinated solvents, of the sort that would be used in the tannery or in metal processing. And what you would put in the treatment area of my reactive barrier is iron filings. So as the groundwater flows through, the iron reacts with the chlorinated solvents. It's not quite a catalytic reaction because there is a bit of consumption of the iron, and the chlorines are stripped off the solvent, and ultimately what you get left with is chloride ions in the water and ethylene, which then readily breaks down biologically. So in that particular case, it's chlorinated solvents with iron filings, but you would match up the contaminant with what you put into your treatment zone. Their trade name is a funneling gate. So the funnel directs the groundwater into the gate, and the gate has a treatment process in it that reflects whatever the contamination that's coming down to it. It's really nifty because groundwater moves under gravity, so all the hard work is being done naturally. The alternative is to pump all that water out and treat it, and that is a very, very energy intensive operation.
Thank you. There was a question here.
Very briefly, you gave a list of sites. You said Weston. Would you be able to identify that geographically?
Weston is a village near Runcorn, and if you look in the literature, you'll find that ICI had a quarry in the area, and the short story is hexachlorobutadiene migrated from the quarry underneath people's properties and into the properties. There were reversible temporary effects on people's health. ICI bought the properties, evacuated the people, treated the land, and resolved the issue. There was and I can say that with a very clear conscience because I studied it, but I wasn't involved in the case. There was a TV documentary on contaminated land, and Weston was one of the case studies talked about. And it began with a sort of dark satanic mills shot of the countryside in the area. And it concluded with the words that ICI did everything that could have been expected of them. And I think one of the big things that they did very, very well was their managing director turned up to public meetings. And you can imagine people were very concerned. It was a very emotional event. And he basically took the flak, took the questions, and provided the answers. And gave confidence that actually they were doing what needed to be done to protect people's health. So that's the Western Quarries case study.
Thank you. We have a question over here in the middle of the room with the blue shirt, please, and then we'll move to the back of the room.
Thank you again for a wonderful presentation. You clarified very well the sources and pathways as well as the receptors that are involved, and they can obviously be quite complex. I'm wondering if when you are asked to investigate a site, exactly, or not exactly, how does that site get defined? Because if, for example, you end up disposing of a contaminant, given the various possibilities in geology, you could well draw in other contaminants from a much wider area. So I'm wondering how the site gets defined and just how broadly this can go.
Can I answer that in two ways? In a planning context, somebody wants to sell the land or build on the land, so they own a parcel of land that they need to have understood. So that's how the site is defined, but you would also look at the surrounding area to see if there's anything that could affect your site, and whether your site could affect somebody else's property or a nearby stream or whatever it happens to be. So that's planning. Under Part 2A, the local authority's duty is to inspect its whole area from time to time, is the wording. And they will take it kind of depends. You would look at an area and you'd say, right, this used to be an industrial estate, or this used to be a big factory with landfill associated with it, product stocking area and so on. So the area will be defined by land use activity, perhaps. You could also look at it in terms of the receptor. This is the footprint of my vulnerable groundwater. But once you've established the size of the source, the nature of the pathways, and then what your receptor is, site is then defined by ownership. So if there are 100 properties that are all affected by landfill gas from one landfill, you actually have 100 sites. And 100 notices will be served for each of those properties. Now, if your footprint of the linkage was smaller than the ownership, then your site could well be a subset of ownership. So does that answer your question? Okay.
Thank you. I believe there was a question near the back over here, please, as well.
Can I ask, do you think local authorities who have a responsibility to check out all the land that they're responsible for, is it being driven by planning applications rather than the priority of the contamination of the land itself because of financial constraints?
The local authorities have had 15 years or 14 years now of implementing systematic inspection strategies to go and look for current problem sites. So given the current land use, is there a problem? And by and large, they've done a pretty good job at spotting the obvious ones and moving through the process of remediating. And it's not perfect, it could be better, but they've done pretty well. So at the moment, most of their work is in looking at planning applications to make sure that what's coming in is, if there's an issue with contamination, that the proposal will recognise that and deal with it in the way that we had earlier on about building houses on gasworks. So a large part of their current workload is supporting their planning colleagues in making sure that land is indeed safe for the new use, while they've still got their inspection duties under Part 2A as well.
Is there a final question? Edmund here has a question. Yes.
Thank you. You mentioned Love Canal and Superfund. That's federal money being spent in terms of public good and cleaning up land. Is there an analogous way in this country that somebody takes a similar view, and it therefore builds on this last question, in terms of remediating land which is not the subject of development now, but could be in the future?
Right. Superfund's origins were not federal money. It was a industry-generated pot of money that was administered by the EPA, but they kind of spent all the money before they dealt with their problems. So now it is federal money, but it wasn't originally. The situation now in the United Kingdom is we have a teeny weeny pot for discretionary spend from the Department of the Environment down to the local authorities. It used to be much larger, and this year it's down to a few £100,000. So effectively, as of today, we don't have a fund like that in the United Kingdom. Northern Ireland doesn't have the legislation. Scotland, Wales and England do. England kept its pot longer than Scotland, and I honestly can't remember what Wales did. But as it stands today, we have effectively nothing at the government level. Some local authorities, and they are a very, 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 very small number, have decided to set aside some of their own internal funds to deal with things like that. But it's almost well, it's pretty much the exception that proves the rule.
Okay,
So remediation is the subject of new application for use.
The vast majority of remediation has always been for reusing land. The initial work that was done back in the 1970s by something called ICRCL, the Interdepartmental Committee for the Redevelopment of Contaminated Land, arose because in the post-war redevelopment initiative, people began stumbling over contamination issues. So the whole initial driver in the UK was about reusing land for development. It's actually quite a late innovation to actually look at land in its current state. One of my research students looked at the Public Health Scotland Act of 1895 or 97, and it had in it all the elements of source, particle, receptor, unacceptable risk, polluter pays and stuff like that. And we got very excited, 1890s. And I said to her, right, how many times was that legislation used by an authority to force remediation? 100 years, never used. She couldn't find any cases of it being used. So we've had the powers, a bit like my Inspector of Nuisance from 1875. By and large, it wasn't really done in terms of general environmental pollution in that way.
Well, thank you for those questions. We now like to bring the evening to a close, but to invite you, those of you who can stay, for a reception in the lower library outside. Paul will be there, able to answer other questions which might come to mind on a more informal basis. I'd like to ask you to join me in thanking Paul and thanking RAW for their sponsorship of this event. Thank you.